Variation of parameters. Consider the linear differential equation with constant coefficient a y double prime plus b y prime plus c y equal to f of t. And suppose the homogeneous solution is y homogeneous equal to c1y1 plus c2y2. We assume that the y particular is going to be equal to v1 y1 plus v2 y2, where v1 and v2 are functions. And this construction is possible where y1 and y2 are linearly independent and forming the fundamental set of solution for the homogeneous equation. Find the derivative of y particular. That's the y particular prime is equal to v1 prime y1 plus v2 prime y2 plus v1 y1 prime plus v2 y2 prime. This is given because of the product rule. We would like to avoid second derivatives of v1 and v2. We may impose an additional condition without changing the final result. That is, we assume that the two terms that have v1 prime and v2 prime, which are v1 prime y1 plus v2 prime y2, they add up to 0. And this helps us with the second derivative of yp prime because the fewer terms are going to show up there. That is, yp prime is going to be v1 y1 prime plus v2 y2 prime, and therefore yp double prime is going to be v1 prime y1 prime plus v2 prime y2 prime plus v1 y1 double prime plus v2 y2 double prime. Now substitute into the differential equation. I rewrote the forcing term on the left side because then we can set everything up equal to each other. So f of t equal to a y double prime plus b y prime plus cy. That is a times the second derivative of the yp, so plug that in, plus b times the first derivative of yp, plus c times the yp itself. Now let's clean this up into groups. One group that each term contains v1, and we factor v1 out. Another group that contains v2, and we can factor v2 out, and the rest. So what contains v1 are these terms, and what contains v2 are these terms. What is left is going to contain v1 prime and v2 prime. Now, what contains v1 after factoring v1 out is just plugging in y1, which is a homogeneous solution, into the equation, which is going to give us 0. And what multiplies v2 is just plugging in y2 into, which is a homogeneous solution, into the equation, so it's going to be 0. And so what is left out is this. Set that equal to f of t, or it was already equal to f of t, and then divide by a to solve for these two terms added together. Now, to determine the y particular, we have to find the function v1 and v2. We solve for v1 prime and v2 prime in the system. One is a condition that we chose in the beginning, v1 prime y1 plus v2 prime y2. And the next one is the condition that we got by plugging in the variation of parameter form of the y particular into the differential equation. Now, again, I want to remind you that these are basically two equations in two variables, and the variables are v1 prime and v2 prime in both equations. You could basically solve for one and substitute in the other, and then solve for that equation, or you can use Cramer's rule, and from Cramer's rule the v1 prime is going to be the determinant of the matrix. First column are the constants, which are 0 and f of t over a, and the second columns are coefficients of v2 prime, y2 and y2 prime, and the denominator is the determinant of the coefficients, which are y1 and y1 prime in the first column, y2 and y2 prime in the second column. In this denominator also is called Wronskian with a W, And then v2 prime, similarly, the denominator is going to be the same, the run scan, and the numerator is going to be basically the coefficient of v1 for the first column, y1 and y1 prime, and then the second column is 0 and f of t over a, which is the column of the constants, and you find the determinant of that. So this is going to give you v1 prime and v2 prime, but to find y of p, I need v1 and v2. Again, here, this is how you spell Wronskian with a W, and this is how you denote the Wronskian. W of y1 and y2 as a function of t. Wronskian is a function of t. So now, according to what we just did, v1 prime is going to be minus y2 f of t, a times this Wronskian. Also, you can denote the Wronskian this way. And then v2 prime is equal to y1 f of t over a wt. Take the integral of this. So v1 is going to be the integral of that minus y2 f of t over a times the Wronskian dt. And v2 is going to be integral of y1 f of t a times the Wronskian dt. And then, therefore, v1 y1 plus v2 y2, which is the y particular, is going to be minus y1, the integral of y2 f of t over a Wronskian dt, plus y2 integral y1 f of t over a times the Wronskian times dt. This gives a particular solution. This solution is unique up to the addition of a solution of corresponding homogeneous equation.